In this video, I'm going to explain about data distributions. Here we see two vectors. Actually, it's a vector with a certain length of 10. And we have four processors. They are denoted by colors: white, yellow, red, and blue. And we have to divide this vector over four processors. There are different ways of doing that. We would like all processors to have about the same number of vector elements. And here we see that on the top we have a block distribution, and on the bottom it's a cyclic distribution. And they are different. We're going to analyze them. So the block distribution you obtain by cutting up the vector into pieces of equal size. And the block size, which we call B, is then n divided by p, where n is as always the length of the input vector, p is the number of processors. We divide n by p, but we round up so that one processor or more processors may have an element more than others. So that's the block size B. And then the formula for assigning a vector component xi, so I is the index of the component, will be that processor I div B will get that component. And div is the division operation where we round down. So I divided by B and then rounding down. An example would be that component 5, in this case we have a block size of 3. Component 5 would be 5 divided by 3, which is 1 if we round down. So then processor 1 would get that element. So a question to you is, how many components do all the processors get if the length of the vector is 9 and we have 4 processors as before? Well, the answer is that the block size is 9 divided by 4, rounded up. So 9 divided by 4, 2.25, rounded up is 3. So we assign blocks of 3 to the processors. Processor 0 gets 3, processor 1 gets 3, processor 2 gets 3, and then processor 3 gets 0 components. So actually it looks like we don't need this fourth processor. So the load balance, which tells how well spread the data are, is determined by the processor that has the most data. And in an algorithm, it is determined by the processor that has most work. In this case, it's 3. We assume that every data element has some fixed amount of work associated with it. So if we want a good load balance, it means that this maximum amount of work should be close to the average, which is 2.25. So it's not perfect load balance here. If, on the other hand, we would do it slightly differently, it's a variant of the block distribution, then we would say, OK, the first processors get 1 more. Everybody gets at least 2. And the first processor gets 3 instead of 2. Here the maximum still is 3. It's just as good as the first one, but maybe you may not like the free rider that doesn't get any data elements. But in terms of load balance, it's the same load balance. OK, so the cyclic distribution is in fact a distribution that card players know by heart. They do it blindly. They assign 0, 1, 2, 3, 0, 1, 2, 3. And it doesn't matter how many cards there are. This system works well. You get the best possible load balance. And mathematically, it means that a vector component xi is assigned to processor I modulo P. So we are counting modulo P. And for example, if I have 4 processors and I have element 7, then this is assigned to processor 7 modulo 4, which means I need to subtract multiples of 4, and the result is 3. So processor 3, which is the last processor, will get that component. So if we would start counting, we start counting at 0, but if we would start counting at 1, then this formula would be more complicated, because we would have to add 1, subtract 1, and then add 1. So that would be a bit more complicated. The formula becomes very simple if we just start counting at 0. And that's actually what some kids that I know of have been raised to start counting 0, 1, 2, 3, instead of the more common 1, 2, 3. And this particular kid now works in C, the programming language C. OK, so as a summary, we have 2 distributions that both are useful in parallel computing. And you may sometimes use one, sometimes the other. It depends on the situation. And both of them assign a maximum of b equals n divided by p, rounded up, vector components to a processor. So they have the same maximum number of components per processor. My final question to you is about a situation where we compute with a vector x, but the number of operations to be carried out for a component xi depends on I, the index, and it actually is I squared. So if you possess component 3, you need to do 9 floating point operations, 9 flops. If you have component 4, then this component causes 16 flops to be carried out. Now, the question is, if you want to achieve good load balance, which distribution of the two would you use? The block distribution or the cyclic distribution? And why?